Translatotron 3, I think that's how you say it, is a model released by, or rather not released, a paper released by Google, Google Research and Google DeepMind. And it basically, the idea of this model is to do speech-to-speech translation, in this case with monolingual data. So given some speech, directly translate the speech to a different language. So maybe in this case, given English or Spanish, translate that to the opposite language, so Spanish or English, depending on which one you're given. So an example is down here.
Creación de nuevos escenarios legales.
And this would be the
Creation
translation.
of new legal scenario.
And you want to do that directly with a model. So given the Spanish speech, get the English speech directly. And they do this with monolingual data. So Translatotron 2 did this with paired data. This is with unpaired data. So you just given a data set of English and given a data set of Spanish, they don't have to be pairs. So the English doesn't have to be paired with the Spanish, which is very cool. And you can see an example of that kind of working down here.
Sí, creo que puedo hacer eso.
This
Yeah, I think I can do this.
is like, it's a good translation, but it's very off from like a reference that they have.
Yeah, I think I can do that.
So like the voice is different, and the translation is also different from the quote ground truth, which is kind of cool. But to start off, I want to go over Translatotron 2, because Translatotron 3 is basically Translatotron 2 with an added loss and a few other parts to it changed. So Translatotron 2, I don't know if this was made by Google or not. I feel like it probably was, but I'm not entirely sure because they don't have that. They don't have Google listed up here. Anyways, Translatotron 2. It looks simple, but it's actually quite complex, even though they only have 4 boxes. So to start off, basically you have a spectrogram. So we want to do Spanish to English translation. This case, it is paired. So Translatotron 2 is paired data. You have Spanish not text, Spanish audio, and you want to directly translate that to English audio, and you have that paired data. So to do that, you first create a MEL spectrogram, as you do with audio. So you have some spectrogram here, and this will be our source, and this will be our target up here. So you have some spectrogram, and the spectrogram, draw that in black. The spectrogram has time and a number of bins. So basically you have some waveform here. And you basically do a windowed spectrogram, so transferring it from the time domain to the frequency domain. And the number of bins is basically how many Fourier features you take for this window here. And you do windowed because you obviously can't get global Fourier features for a audio waveform. That wouldn't make much sense because Fourier features are very sinusoidal, repeating, while an audio waveform is not. So you take the MEL spectrogram here, and that'll be used just as an input. So the MEL spectrogram is basically just an image, just a normal old spectrogram, and you throw this through an encoder, and they say that the encoder it takes the MEL spectrogram of the source speech as input and produces a hidden representation which encodes both linguistic and acoustic information from the source speech. So basically we just want to encode this somehow, as opposed to using the raw data, we need to encode this. So to do that, they have this fancy looking encoder, and it's called a conformer. Conformer. So you have these conformer blocks here. So conformer. And you stack these like a transformer, and a conformer block is composed of a bunch of parts. So you have some feed forward layer, and so you're just trying to encode this. This is you can think of each part in time as like a token, in a way, that you're encoding with a transformer, except it's for audio. So maybe you have some special blocks in here. So you have a feed forward layer, And then, yeah, you add the output of the feed-forward layer, so just a residual connection. And of course, you have to have your multi-head self-attention layer, as you do. What model would be complete without your self-attention layer? And residual. And then you have a convolution. And then you have a layer norm, like so. And you just stack these blocks. So you basically captured global dependencies with your multi-head self-attention, and then local dependencies with a convolution. And I think that's, oh, you have a feed forward right here, and then a layer norm, feed forward, and then a layer norm right here. Whatever, there. So yeah, that's a conformer block, and you basically just stack these and you get your encoder. So the output will be some dimension by some time, by some factor of the time. And these are your latent outputs, which have your global dependencies and your local dependencies. So a rich representation for your spectrogram. Now, this attention part here is actually they make a big deal about it. So it's just a one layer attention, and we'll get back to that in a second. But yeah, we'll get back to this in a second. So what you do with your decoded, or what you do with your encoded MEL spectrogram, your features, is you're going to throw this through attention. So an attention mechanism, which we'll get to in a sec, and the output of the attention mechanism is going to be sent through this decoder here, and this decoder is basically going to extract phenomes, and it's going to do it autoregressively. So a phenome is basically just like it's basic parts of speech. So you can think of this as like a transformer predicting text. So it would predict it one word at a time. So it would predict the, cat, sat, and so on. You have a vocabulary, it's discretized. The phenomes are exactly the same, except it's for speech. So you're just predicting this sequence of phenomes in the source language, or in the target language. Now, to do that, you are going to use they use an LSTM, and they mention that attention-based speech generation is known to suffer from robustness issues such as overgeneration and undergeneration. So I'm guessing that's why they use an LSTM here rather than a attention mechanism here. And they just use one layer of attention here, because you could definitely use attention for this. It's just like a speech generation, but they use an LSTM. Now, these two go together. So these are going to be the queries. So you're going to be producing queries using the decoder, and your keys and values come from your encoder. So these will be your keys and your values. And what the attention decoder module kind of looks like is, so like I said, it's one layer attention, and it's going to be a cross attention layer, basically. So what this looks like is you have your source here. So you have some, we'll call this this will be our source, and this will be, say, m by d. So some dimensionality m by d, and your attention mechanism is basically going to take in your, and these produce your keys and values. It's going to take in your current sequence that you've decoded, your current phenome sequence. So you have your attention here. And let's say we start with one token. So this may be the first token in your phenome sequence that you produce. In the text equivalent, this would be like the word the. This would be your first token in your sequence, or maybe it'd be a start token. Start token. And you send this through the attention mechanism, and you condition on the keys and the values. So that will output a sequence of the same length as this. This is a 1 by d sequence, or n by d, where n is equal to 1. And it'll output just the single token with this cross-attention conditioning on it. So this will be 1 by d as well. And you then send this through your LSTM decoder, so LSTM. And you have your hidden state here, and your LSTM does its thing, and it'll output the prediction for the next phenome or next word in the text corresponding case. So this may be like cat, but the phenome version of that. I'm not sure what their vocabulary is, so I'm just going to use the text instead. After that, you then send this through, you then concatenate this with your original token, and you get out a sequence of shape n is equal to 2 by d. And then you repeat this process like you do with a normal autoregressive strategy. So attention, you send these tokens through there, conditioning on the source, again, keys and values. So this conditioning is just going to be on this attention module is basically just conditioning on the source sequence. And you'll get out your 2 tokens, and you're going to send this through the LSTM again, just this token. Oh, this outputs a hidden state, call it H prime. And then it'll output the next phenome. I'm just going to use a word instead. And then another hidden state. And so on until you produce your sequence of phenomes, or your sequence of phenomes. So whatever that may look like for this vocabulary. So English phenomes, you produce that using this decoder here, using this attention module first, and then this LSTM module up here. They make a big deal about the attention. So down here, they say, this attention does not directly model translation alignment between 2 very long spectrogram sequences. So you're not modeling attention between 2 spectrograms, which is a problem I think they had in Translatotron 1. Instead, it models the alignment between a source spectrogram sequence and a shorter target phenome sequence. So they basically kind of wanted to compress this a little bit, and you compress it because you're modeling a phenome sequence and a spectrogram as opposed to 2 really long spectrogram. And what this looks like, I'll draw it out. So the attention matrix is going to look like this, or something like it. And these will be your queries. Your queries in R, we'll call this n by d. So this is going to be these are going to be your phenomes. Yeah, these will be your phenomes here. And then your keys in are m by d. And this will be your source. Like that. So what each token kind of models, so this is basically like a new phenome token. The output is basically going to be like what parts of the source make up the phenome. So you're going to get a linear combination where the source your source basically creates a linear combination, or your phenome is composed of a linear combination of the source and the output. So the output is linear combination of the sources, and that basically represents how does this phenome here make up the source. In a way, that's kind of how you can think about this, and that's why it's important to have at least one attention module with this cross attention. And it basically just conditions it, the sequence on it, your current sequence on it. But intuitively, or kind of intuitively, this basically just models, or this basically just represents, each token represents how this phenome is composing the source. So there's kind of some interpretation there. Now, once you have your phenome sequence, after you have used your, after you've sent this through attention and your decoder, and you've done it autoregressively, you then send this through the synthesizer. So you have this phenome sequence, you have this source condition sequence, and you're then going to send it through this this synthesizer. Oh, and the queries are just directly from the decoder. Like those are just the direct outputs transformed by the queries. So now that you have basically a source condition sequence and a phenome sequence, you can then create a you can then combine these together and do synthesis of speech. And you basically are just going to want to produce a spectrogram. It's just a spectrogram of the English text, or English speech in this case. To do this, they don't just take the raw phonemes, as that doesn't have any information of the source. They combine the two parts here, represented by this arrow here. You take the output of attention and the output of the decoder, and you send that through the synthesizer. So you concatenate them, output of the attention mechanism and output of the synthesizer. So, I mean, the synthesizer is going to output a sequence of phonemes. Each of these are sent through a linear layer and then a softmax layer. So you take the outputs before that, the latents before they're transformed into a distribution over all phonemes for each part. And the sequences are going to be the same length, the output of the attention mechanism and the output of the decoder, because those are the input into the decoder is the output of the attention mechanism. So they're going to be the same length, and you can just concatenate them along the dimensionality axis. So we'll call that N, because the output is going to be the same shape as the decoder. And this first one is going to be the decoder output. You can concatenate them whichever way. And this will be your raw phonemes. These are your outputs from your decoder. And the second part is going to be the outputs of the attention mechanism. And these will be your source. This will be your source condition phonemes. So source condition phonemes and your raw phonemes. And you just concatenate them along the dimensionality axis, or along the dimension axis. You then have this duration predictor. This is just some fancy LSTM. They say that they use NAT. It specifically is made to not use attention. So if you're curious how the duration is predicted, they do that. But basically, you're predicting a duration for each phenome in the sequence. And that basically says how long is this phenome going to be spoken for. So you have some phenome, and how long is the phenome going to be said for. You then upsample based off that. So if I have say 3 phenomes here, and maybe I'll just do this based off seconds. So I say, oh, this is going to be 1 second, this is going to be, say, 2 seconds, and this is going to be, say, 3 seconds. Then you would take the first one, color code these actually, like that. You'll take your first one, you won't repeat it at all. You'll take the second one, you'll repeat it twice, and then you'll take the third one and repeat it 3 times. And that's just your upsampling based off the duration. And then you send this through an RNN, a convolutional RNN, and you autoregressively produce the output spectrogram. So some spectrogram here. And yeah, then you just predict the English spectrogram using this part of the synthesizer. So you basically give it the repeated phenomes, and it decodes those phenomes into a spectrogram using an RNN. I think it's just a convolutional LSTM. I think that's what it is, and you just autoregressively do that. And that'll give you your spectrogram. I think they do this using a regression task because they have an L2 loss. I'm curious if you can use residual vector quantization to make this a probabilistic task as opposed to a regression task, because transformers and stuff work better. They seem to work better with a probabilistic classification task as opposed to a regression task. Anyways, they model this as a regression task, so it outputs each part of the spectrogram. So it output this first part here, and the next part, it's kind of like you just output each part, and then you have your output speech. So yeah, that is the Translatotron 2. Now on to Translatotron 3. So, no, not that one. This one. So Translatotron 3 is very similar in that it uses the exact same thing, except it's different in that it uses 2, and we don't have, like I said, we don't have pairs. The idea is we don't have pairs of English-Spanish text, or English-Spanish, or whatever languages audio. We don't have those pairs. We only have a source. We have a bunch of English audio. We have a bunch of Spanish audio, but we don't have a relationship between them. And you can think of this as CycleGAN. If you've heard of CycleGAN before, what they do here is similar, because in CycleGAN you don't have the pairs. So this model looks very familiar because it's just Translatotron 2. So this part here, that's all it is. Translatotron 2. So they add a few more things to it. So first off, they add this thing called Muse. I think it's Muse here. And then they add, they basically have 2 models. So they have 1, and remember before, for Translatotron 2, we went from source to target. They basically create 2 Translatotron 2 models, one going from source to source, and the other going from target to target. And you train these separately, so this may be just on like English, and this may be on Spanish. You train these independently, and then you combine them in a second stage, basically having a consistency loss between the 2 models once you have trained these independently. So before you get into how that works, they have this Muse loss, and the Muse loss they make it's actually pretty important. If we look in the ablations, they basically want to find a relationship between the 2 languages. The idea is we're going to have an encoder for both languages. So we're going to have an encoder. The encoder is going to be shared for both languages, and the problem they run into is that the encoder is actually not good enough. Like just training this normally on an L2 loss isn't good enough if you just let the encoder do its own thing. So we're going to help the encoder by introducing this Muse thing. So Muse is just a linear mapping between, or they call it I think they just call it a simple mapping. So maybe it's not. Here they show it's linear, but maybe it doesn't have to be linear. But yeah, you basically find a mapping W between your 2 languages. So if X is an embedding for English and Y is an embedding for Spanish, then you want to find a matrix W. So if this is in, say, RD, you want to find a matrix W, which is in D by D, such that the L2 norm between these 2 are minimized. I guess C by C. And that'll be your optimal W here. So you're basically going to find an optimal W, so a linear transform, such that the Frobenius norm between the language embeddings is minimized. That's basically what you're doing, and they do so using an adversarial approach. And they show down here that they have some loss function, assuming you have a discriminator that is a simple classifier that is trained to predict an embedding originated from the source or target language. So assuming you already have this discriminator, I can classify if an embedding is from which language. You can then use this loss function here to train your single weight matrix here, such that x and such that the transformed x by w is as close as possible to y. So maybe you want pairs of language here to minimize that. So to do that, you basically just here. This first part here is maximizing the probability that the transform x is the target based off the distribution predicted by the discriminator, or based off the probability predicted by the discriminator. And here, there's a negative sign in front. So maximize the probability that yi is from the source. So yeah, it's just normal old adversarial training, assuming you have this discriminator. Assuming that your discriminator is good, then you will have a W matrix that is very good at producing the Y, so producing the corresponding Spanish embedding vector given some English embedding vector. Now, there's two problems with this. This assumes one-to-one mapping. It also assumes a linear mapping, but apparently it helps the model quite a lot. And I also think that's another problem, that you need this for the model to do well. I feel like it's kind of it feels a bit weird introducing this into the model. This also restricts the model because it can only go from two. It can only look at two languages unless you do something strange with it. Maybe you introduce another W star, another optimal W. But yeah, this only allows one-to-one correspondence between two languages. So this feels a bit strange. Now they throw this on the output of the encoder right here. So before in Translatotron 2, you just had the encoder. It produced some representation off the spectrogram, and then you would decode it into the output spectrogram. Now, this Muse loss is introduced here, and basically assuming you have an optimal W, you've trained your Muse W parameter, or you've trained your Muse W matrix, you have this Muse loss here. And the Muse loss is basically just an L2 loss between the output of the encoder and the Muse embedding right here. And you just do that for some n. Specifically, they only do that for half the output of the encoder. So it's not the entire output, just the first half of the output of the encoder. So the encoder outputs some matrix here, and you split that down the middle. And these are Muse optimized. They have a penalty for the Muse loss. So basically, they have to be close to the Muse embeddings, and these do not have to be. So whatever, they find that works better. So that is a thing they do. I'm guessing, or they mention that the encoder finds, like it may weigh one language over the other, but Muse forces it to not do that. So if you add this loss here, so it doesn't kind of lean toward one language over the other to optimize this. But yeah, it feels like a weird way of doing that. So that's the encoder. Now the decoder stays the same. Yeah, they mentioned it has teacher forcing, which is just, they had that in Translatotron 2. Teacher forcing is basically instead of training the model where the output of the LSTM, so the output is sent back into itself to make another prediction, to make the next prediction. Oops. LSTM. You instead take the ground truth output and send that through. So you have some ground truth output. You don't do this connection, and you instead send the ground truth in during training. So yeah, we have a decoder. We have a decoder for both, and basically the output of these is just going to be the source and the target. So we have our source spectrogram. We predict the source spectrogram. We have a target spectrogram, and we predict the target spectrogram. And the losses are just L2 losses. They also have a phenome loss, which Translatotron 2 also had. Basically, just like I said, the phonemes are like English or like decoding, and it's like decoding a sentence in a way. It's like decoding a sequence of words, a sequence of tokens. So you already have those phonemes. You can have a loss for those. That's just normal cross entropy loss, and this is just normal L2 loss between the spectrograms. And here you basically train one model to reproduce the source spectrogram and one model to reproduce the target spectrogram. And these are just Translatotron 2 models. More formally, they have them down here. So you have, where is it? Right here. So you have this spectrogram loss. So given a spectrogram, a target spectrogram, and so a predicted spectrogram and the actual spectrogram, the ground truth, you basically just do an L1 and L2 loss. My bad. It wasn't just L2. It was L1 and L2 loss over the spectrogram, and you just average it over the time and the number of bins. So normal loss. And then your oh, my bad. These are not. These are your duration loss. So your duration loss, I forgot that was also a part of it. So the duration loss is basically just the L2 between the predicted duration and the actual duration. So you have that for your decoder. You have that in your decoder. And then you also have the phenome loss. So the phenome loss is just your cross entropy loss, like if you had a normal transformer doing autoregressive prediction. So phenome loss between the actual phenome and the predicted phenome, just phenome loss, or just normal cross entropy loss, and you average over all the phenomes. Yeah, and this was in the synthesizer here. Now, this is just training 2 models. We have to connect them somehow. So once we have these 2 models trained, this may be just on English, and this is just on Spanish. With all of these losses here, you can then combine them together. So let's say we take this part here. So we take this part here, and we take the source spectrogram. So I guess it would be this part here would look like that. So we take the source spectrogram, so this would be, say, English. We throw that through the encoder, and remember our encoder is shared, so we can do this. And then we take the English spectrogram and we throw it through the decoder. So this will output a Spanish spectrogram. Yeah, this will output a Spanish spectrogram. So this basically translates it. We then take the Spanish spectrogram and we throw that, so that would be this part here. We take the Spanish spectrogram and we throw it through the decoder for the source language. So we then predict an English spectrogram given the Spanish spectrogram. And the idea is that we want these two to be as close as possible. So this is very similar to CycleGAN, where you want the outputs to be as close as possible. It's just having the consistency between the two be the same. And you have to do this because you don't have one-to-one corresponding labels. So yeah, that's the idea. Basically, after you're done training these, you create this consistency model over here to basically produce a Spanish spectrogram. And to produce a good Spanish spectrogram, or to produce a good English spectrogram, you have to have a good Spanish spectrogram because this was trained on the Spanish data. It would be out of distribution for this to be some other weird spectrogram. So it has to produce a good Spanish spectrogram in order for it to produce a good Spanish spectrogram or an English spectrogram in the end. And the loss is very simple. If we just go over to the loss down here, all it is this back translation loss right here. And the back translation loss is just the L2 loss between the predicted source and the actual source right here. So the predicted source and the actual source, it's just the loss between the English and the English spectrogram, or the Spanish and Spanish spectrogram. And it's just L2 loss between the two. Or the L2 and L1 loss between the two, the average that I showed before. But you also keep in the duration and phenome losses. So all the losses you had before, you keep those in there as well. That's shown here. So you have the first phase losses, which had this reconstruction loss, or this reconstruction loss, this phenome loss, this Muse loss. You keep that in there so that the model retains its behavior, so it doesn't completely transform into some other model. So you keep the losses you had before in order to keep it producing the spectrograms it did before. So they say that, yeah, I think they say that down here somewhere. But that's the idea. You keep those old losses so that it retains its behavior. And then you have the back translation loss. So that's pretty much it. Translatotron 3 isn't too much more complicated than Translatotron 2. It's just two Translatotron 2 models combined together. You have a cycle consistency loss, and that allows you to produce these Spanish spectrograms. And you can now do this English to Spanish or Spanish to English conversion by just taking one part. So you could just take this part, and I can do an English to Spanish conversion, or I can just take this part, and I can do a Spanish to English conversion. And yeah, I mean, it does pretty well. If we look here, it does really bad if you only have reconstruction loss. It does really bad if you only have back translation loss. But once you introduce Muse and spectral augmentation, then it does well. Spectral augmentation, if you're curious, is just this augmentation strategy with three parts. The first part is time shifting. So you take the spectrogram, you just shift it over in time a little bit. So you'd shift the spectrogram over some amount a little bit. And the frequency mask. So you randomly mask out some frequencies. You can just do that by masking out a bin by just removing it, zeroing it out. And then the last part is randomly mask time segments. So we have this time segment here. You can just mask out that entire time segment. And then it has to do the prediction like normal. So some augmentation. Augmentation usually makes things better. And on the benchmarks that they have, I think they only have two. They do well. They do better than the baseline. I think they don't really mention the baseline much, but they do better than a baseline. So I mean, it's hard to say. It's hard to say how well it actually works according to these metrics. Like, it sounds good if we go to their website, but they also didn't release the model either. So we actually don't know if it works as well as they say it does. We'll have to wait for somebody to create the model. And then they have some more metrics or they have some more benchmarks and stuff if you're curious. But that is Translatotron 3. Basically just a cycle consistency loss translating from two languages. Yeah, and that's the paper. We will see if somebody implements this and if it's actually as good as they show. Hopefully it is, because that would be kind of cool. Because it works really well over here, but it works really well on this site over here. Curious if it actually works this well, because it sounds pretty good. Wish Google would open source the model though. Anyways, that's Translatotron 3.